So the last one I'll cover is the ideal Brayton cycle. So if you end up applying the Siemens or some of these places, or some gas, there's a lot of gas turbine, there's a lot of power producing places within Florida. So I give you this so at least you're exposed to this if you ever have a job interview. So if you're going to get a job interview with a company that does things related to gas power cycles or power producing devices, you should review chapter 9 of your thermodynamics textbook, and you should know more than just this ideal case, and you should be familiar with the other forms of the Brayton cycle. Okay? Can't cover everything in class, but remember, apply to something, look in the textbook from your coursework that is related to where you're applying. You don't need to look up research papers, you should look at textbook information for review. They'll probably ask you questions on it. Okay, so the ideal Brayton cycle represents for a closed cycle for a gas turbine engine, and the ideal case can be described by a 4-step cycle process. So let's do it. And A, pressure versus volume. B, entropy, temperature. And isentropic compression in a compressor. So this cycle is not just, it's a gas power producing cycle, but it's not your diesel and your auto, it's not your gasoline engine and your diesel engine. This is more of a compressor turbine combined system. Okay? So there's another diagram, and just don't put pistons in. So you compress a gas in a compressor, and then after you do some other things with adding heat, then the turbine produces work. And as long as less work is going into your compressor, then the work output from your turbine, it's a power producing device. Cycle. So let's start here, 1 to 2, isentropic compression. So we just talked about before, if I compress isentropically, what happens to the temperature? Goes up. So I know I'm going to go somewhere, I can put a T1 here, and I'm going to have some T2 higher.
Is the Brayton cycle one of those where it's easier to start with the TS diagram?
It might be. Given I start here, I'm going to do that. So 1 to 2 compression. So I need to pick a spot here. Now, constant pressure heat addition. So you kind of want to look at 2 and 3 and 1 to 2. So at constant pressure, I add heat, so the temperature goes up. I increase the temperature. What happens to the entropy?
Increases.
So based off of these two statements, we're best off starting down here with S1. And given this is isentropic compression, S2. And then I have constant pressure heat addition. So I add heat at constant pressure. I increase the entropy, I increase the temperature, and I have something that does this to 3. And then constant pressure heat addition, so I have some Q in. Then isentropic expansion. Isentropic. S3, 4. And then constant pressure compression with heat rejection. So yes, this one's much easier to start with the TS diagram. Someone else might say that the other way is. So let's look here. I have low entropy, low temperature. What should be the pressure? Low.
Mm-hmm.
So I'll start here, P1. And I'm doing compression. So I'm going from here to here. So I'm going to be somewhere along this line. So let's just pick right here for 1. And then I have constant pressure heat addition. So I know I'm going to be increasing the pressure. isentropic compression. So I'm increasing the pressure, so I do something like this. This is isentropic. Constant pressure, heat addition. Okay. Now I have isentropic expansion. So I'm going to follow the same type of path. And then constant pressure compression. So isentropic, constant pressure. Okay. So these were the diagrams. Any questions? No? Now, just by inspection of this, if you remember from the diesel cycle, we had this constant pressure with heat addition, so we have some work by the system, we have some work on the system, and we're coupled with heat. So you remember it was a little more complicated, we had to end up using that enthalpy relationship.
Mm-hmm.
So, again, C is, what is the thermal efficiency? What is the thermal efficiency? And the general way of writing it for a work producing device, work net out over QH. And QH is equal to Q in, and QL is equal to Q out. And I can rewrite this as 1 minus QL over QH. And these I can get via first or second law / balance. So let's start with QL. QL is what? Let's use the first law. And QL is Q out. So that's first law energy balance from state 4 to state 1. So this is 4 to 1. So Q in plus work in plus energy associated with mass in 4 to 1 minus Q out, work out, energy associated with mass out, 4 to 1 equals the change in internal energy from 4 to 1, so that's U1 minus U4, which of course is delta U. And I can cross these out. What is the heat in from 4 to 1? I do not have heat in. What is my mass in? Mass out are 0. What is my heat out? This is QL. So I have a minus sign. What is my work out? Now we can use the top-down reading a page perspective. This represents counterclockwise. So this ends up being work in. So I have work in minus my heat out equals U1 minus U4. So I want to write this in terms of QL. So I can just bring that over here. So I'm going to have work in let's do it this way. So minus QL equals U1 minus U4 minus work in,
Raise up.
which gives me QL is equal to U4 minus U1 minus work in. 4 to 1. No, this is work in. Work in's over here. Oh, I transfer the negative to plus. Yes. Thank you. So U4 minus U1, work in. Okay. So I have this expression here. Now, work in is equal to minus the integral of P dV. Work out is, so this is V4 to V1 at constant pressure, which is basically minus P1, V1 minus V4, which equals P1, V4 minus V1. So then when I plug this part in, work in, P1 here, I end up getting, I'll write it in black, QL is equal to U4 minus U1 plus P1 V4 minus V1. This is a constant pressure process, so delta H is equal to delta U plus P delta V plus V delta P. This is 0 from 4 to 1, constant pressure. So my QL, combining these two, QL is equal to delta H from state 4 to, well, it's equivalent to state 1 to state 4. This represents, so I had the minus sign. You saw the minus sign here, where I had to switch it around. So this is equivalent from going backwards 4 to 1, because I did the sign. So multiplying QL by minus sign is equivalent to making it QN, which is equivalent to going from 1 to 4 instead of 4 to 1. So I have this, and then based off of partial H with respect to T, a constant pressure is equal to Cp, I get QL is equal to the mass times heat capacity at constant pressure, and then I have T4 minus T1. Yes?
For the delta H value, delta H equals delta U. Did you product rule the PV?
Yeah, you have to product rule the PV.
Okay.
But then it's constant pressure process, so we can cross it out.
Professor?
Yes?
Since we know it's a constant pressure process, so we know.
You could probably jump all this stuff that I've been doing.
Yeah, so we can just go from.
You can just go straight from right here. See how I have this, or straight from this part right here, where I get all the signs?
Mm-hmm.
Well, I'm saying, can't we just skip finding QL? We know, or it's Q out, right?
Yeah.
So can't we say that it's a constant pressure process?
Okay, so if you want to say for a constant pressure process, constant pressure process, okay? Ideal gas, closed, delta U, all right, Q is equal to delta H.
Just make that assumption.
Constant pressure process, ideal gas, closed system, U is equal to delta H. I just proved it to you.
Now, do we have to prove it, or can we?
Okay, so you can assume it. But this is kind of the proof of that.
Because I know in the diesel cycle, we had a constant pressure process at the top. And
Yeah, with constant pressure, but that was QH, not QL.
Yeah.
Yep. So given that I already did this twice, so I have this QH, right? So I have that. I can do the same. I need to know QH is what, and that's from 2 to 3, as shown here. And then I can just say that my QH is equal to delta H 2 to 3, which is equal to M CP T3 minus T2. I just skip a bunch of steps because I'm just going through the same thing. Now this was minus QL. If we did it before, this was minus QL equals delta H, was going to be delta H, so then we ended up getting this 4 to 1 instead of 2 to 3. But you get the general idea. And so I can do the thermal efficiency of the Brayton ideal case is going to equal 1 minus mCp T4 minus T1 over mCp T3 minus T2, which implies that the thermal efficiency is 1 minus T4 minus T1 over T3 minus T2.
Professor,
Yes.
for the QL, shouldn't it be T1 minus T4 since it's delta T?
There was a minus sign. I'm going from 4 to 1, so let's go back up to here, this equation right here. So my heat in, work in, mass in, minus my heat out, work out. And I crossed off all these things, and I ended up getting work in minus the heat out is equal to change internal energy from going from state 4 to state 1. And so then when I rewrote this, I brought work in over to here, and then I multiplied by minus 1, and multiplying this by minus 1 changes that, puts a positive sign here. And then when I did all this other stuff, because minus QL is going to be equal to delta H 4 to 1, which is the same as plus QL is equal to delta H 1 to 4.
I got you. Thank you.
And so then it's 1 to 4, so my final, so there was just a sign conversion aspect.
Thank you.
But thank you for asking this question about heat transfer and changes in enthalpy. So saves you a lot of math. Constant pressure process, closed system, ideal gas, that works. Even if you don't have an ideal gas, constant, closed system, that's going to work.
And you just make sure that your temperature is like T3 to T2
Mhm.
is a positive number.
Mm-hmm.
If it's negative,
Yeah, so the last thing I wanted to talk about is this one last thing. And it's related to a couple of the past exam problems. And it's related to reversing the Carnot cycle. So this is what we had before. We had this Carnot cycle consists of, and we drew the Carnot cycle. Okay? And then I asked the question below, now if we reverse the cycle such that, for example, we just reverse it around. So let me just draw the TS diagram for the Carnot cycle in the very, very general way. And let's get back to this question. So T S. Okay? In Carnot cycle, I'm gonna be quick with it, and I have a square, and for the standard Carnot cycle, power producing, heat transfer between reservoirs, I have a TS diagram like that, and I know that this is Q net in, and the Carnot cycle is a reversible cycle. Okay, so now we're going to reverse the cycle. So in the black is the cycle that went through. I take my Carnot cycle, my system, and I go through one cycle, so I'm right back to here. So I go from 1 to 2 to 3 to 4, and then back to 1 cycle. Now if I reverse the cycle and go in this direction, and now my process is, I'm going to call it, so this is the cycle, if I do a normal cycle plus a reverse cycle, plus 1 to 4 to 3 to 2 to 1. What is my net heat? This was clockwise. I showed that it was net heat in. Now I'm doing this cycle plus the reverse cycle. Now my system consists of running the system forward and then running it backwards. What is my net heat transferred? 0. That's how I can, so the Carnot cycle says it's reversible, but you have net heat out, right? Or net heat in. When I reverse it, I still get net heat out, but if I go through the process and I can run it through, so now I'll just consider this 1, 2, 3, 4 is stage 1 or process 1, and process 2 is 1, 4, 3, 2, 1. That's my cycle. And I end up with delta U is equal to 0. So for this one here, just call it stage 1 and stage 2, I get net heat out, delta U is equal to 0, and delta S is equal to 0. Now my cycle consists of 2 cycles, right? One normal, one reversed. And given that it was reversible, I know that's the case. So I can have a cycle that is said to be reversible, but I would have to reverse the cycle and see if I have no net heat transfer before I could really say if it was reversible. Or verify. Okay, so now given I have this standard cycle and the reverse cycle, the question is, now we reverse the cycle such that there is, just reverse the cycle. And the reverse Carnot cycle has the same second law efficiency and dead state surrounding temperature. Okay? So I have the same T0 surrounding temperature. And the question is, how do you, given it has the same second law efficiency, how do you compare the entropy generated for these two cases? So what you need to do is you need to write out the second law efficiency for the Carnot cycle, which is power producing. Okay? That is going to be related to the reversible work and the useful work. So for a power producing device, the reversible work out is the maximum achievable. So work, reversible, work, useful. Okay? And for the power producing device, work reversible equals the work useful plus T0 Sgen. Remember the plus sign was power producing and the minus sign was power consuming. Okay, so I have this expression with the plus sign and work useful, and then I could write work useful is equal to work actual. Work useful is equal to work actual minus work surroundings. Now in this case, we're not doing any surrounding work, so I can cross this out. So the Carnot, the second law efficiency for this, I'll write it in blue. Second law efficiency, Carnot, is equal to the work actual, which is the work out, over the work at reversible, which is the work actual, plus T0 Sgen Carnot.
Sorry.
Yes?
How do you know it's a power producing?
The Carnot cycle is power producing. Yeah. So if I were to tell you how you draw in a PV and TV diagram, just like I did in the previous problems, when you drew it, you would see when you draw it on the PV diagram that it's clockwise and it's net workout. But just for your information, the Carnot cycle is a power producing device. The ideal heat engine, where you take heat from a high temperature source, a volcano, and you reject it to a low temperature source, an ocean, and you get work out of it. That's the Carnot cycle, power producing. So I have this, and I want to know, is Sgen of the reverse cycle greater than, equal to, or less than the entropy generated of the standard cycle. So I gave you these expressions to write out the second law efficiency. I said when I reverse it, I get the same it has the same second law efficiency. So this was for my power producing. For my power consuming, I have the second law efficiency is equal to the work reversible over the work useful. Again, work useful is equal to work actual minus work surroundings. Again, this is 0. And my work reversible is equal to my work useful minus T naught S gen. So when I write this out, second law efficiency for my reversed Carnot is going to equal, now you can see here that useful is equal to actual. So this ends up being work actual minus T naught S gen over work actual. So I have these two expressions. And I'm asking to compare S gen. And I said that the second law efficiency for both processes was the same. So I can equate these two expressions, or I can rewrite them in terms of S gen. And okay? So I can equate them and then rewrite them in terms of S gen. Sometimes what I think will be easier, I can go through the algebra. But let's just, before I do that, let's just plug in numbers. So if I know the area under this curve, I know the area for the work. So the regular Carnot cycle, this direction, gives me the work out. If I reverse it, it gives me the work in. Okay? So I know the magnitude of work out has to equal the magnitude of work in because it's reversible. So the magnitude of work in is equal to the magnitude of work out. And the work in was for the reversed Carnot, and this is the standard Carnot. So I could just plug in here works, right? Just W's for actuals. They're all the same. And I know these are the same. So let's just do the algebra. So I have eta 2, so I have work over work plus T naught S gen Carnot equals, that was the one from above, and so then I have work minus T naught S gen reverse over work. So I can go through and I can multiply through and do a bunch of stuff. So let's just take this and bring it over here. Let's take this and bring it, well, yeah, and then let's minus this from both sides. So I have a minus. Okay.
Can you move it up there?
Yeah, I can minus it. I already brought this over.
No.
Well, not on top though. Yeah.
Can you move the paper up?
Yes. So I have some expression like this. So sometimes it's easier just to plug in numbers.
Can we try that?
Yeah, let's just write this one right here in terms of S gen reverse. So I have the second law efficiency, okay, times the work is equal to the work minus T naught S gen. So from this, I can get T naught S gen is equal to the work minus the second law efficiency times the work. So S gen is equal to the work minus the second law efficiency times the work over T naught. So let's just say T naught equals, well, let's use 300. Okay, for 300 Kelvin. And let's just say the work is equal to 50. So we can say equals Kelvin and 50 joules. And the second law of efficiency is equal to 50%. So we plug that in, and remember this is for the reverse case. So we plug this in, and I got 50 minus 25 over, let's make it 1. 50 minus half of 50, so I end up getting 25 joules per Kelvin. Now I go up to this one right here, and I rewrite it. And when I do that, I get work actual times the second law of efficiency plus the second law of efficiency times T naught S gen Carnot equals the work actual. So then I can say the work actual minus the work actual times the second law of efficiency divided by the second law of efficiency divided by T naught is equal to S gen Carnot. Did I do that algebra right? Yeah, so I did all that right. And so then when I plug this in, I can plug in numbers. Now again, the work is still 50, and the temperature is still 1, and I still have the same second law of efficiency. So I have 50 minus 50 times 0.5 over 0.5 over 1 equals, so I have 50 minus 25 over well, this is divided by 0.5, so over 1 times 2, which equals 50 joules per Kelvin. So basically, the entropy generated for the standard Carnot cycle is going to be greater than if I could reverse it, the reverse Carnot cycle. So the only way I can have that same second law efficiency of a reversible process is that I reduce the total amount of entropy generated for that process to work. So back to this question, what statement is true for the, in comparison to the original? Well, this has to hold.
I was going to ask you, so is that true for all power producing devices? That a power producing
Yes,
device?
that's another great question. So what that means is, if I have a reversible power producing device, it's always going to produce more entropy than if I could reverse it in a reversible case. Which means that it's going to be harder to reverse it, because in general, if you try to design something, it should be easier to engineer something with more entropy generated instead of less. So if you design something that works a certain way and you try to reverse it, it's most likely not going to be able to be reversed, because that would be fundamentally saying that you're going to reduce the entropy generated. So I really like this problem. It takes a little bit of time, but it shows you that gets back to this delta S can be equal 0. It gets back to the delta U equals 0 for cycles. It shows you if you have a reversible cycle, if you reverse it, you need to follow the exact same path so you have no heat transfer. And it shows you how to use these relations related to the second law of efficiency and couple them to the entropy generated and the actual and useful work. Yes?
So if we reverse the power consuming cycle, would the reverse still be half less energy generated?
No.
Oh, so it's always power producing?
It's always going to be towards the power producing. But on that note, so when you're reversing things around, We can say it. I'll just ask. It's going to want to go towards that one direction. And the main reason for that is because of the temperature reservoirs.
Yeah.
It's easier, so entropy says that heat goes from high temperature to low temperature. So if I just flip this over, and here I have my cycle, and if I have heat going in this direction, from T low to T hot, and in this case I have to put work in, this is against the natural direction that heat flows. So in order for me to have the same second law efficiency, I need to produce less, I have to have less entropy generated. So in principle, to go against the natural laws of nature, second law, I'm going to have a lower efficiency because I'm going against the natural trend. Heat wants to go in this direction. We made a refrigerator to go against the laws of nature. So we would have, in consequence, it would always be a slightly lower efficiency. Or with equal efficiency, that would mean we would have to have a system that would produce less entropy generated. Any general questions? Yes?
For the cycle analysis, did you choose the process 4 to 1 and 2 to 3 based off the PV diagram because they're constants? You get the constant pressure.
Which one is this?
I guess the Brayton cycle, but pretty much for all of them, like why did you choose the processes that you chose from either 4 to 1 or 2 to 3?
Oh, okay. So you're asking when I did this analysis here, why did I choose 4 to 1 and 2 to 3?
Yeah, when you did the first law analysis.
Because this is the only place where I have heat in and heat out, and this expression here, I rewrote it, the thermal efficiency into heat transfer. So all I did is looked at the diagram and found the stages of the process where I have heat transfer. And that's the only place I need to do energy balance. Now in principle, I could get the whole area under this curve, right? Do the whole cycle and get the network out. And then know what the heat in is. But I just simplified it, and I only need to do analysis over 2 states because that's how you get the thermal efficiency. Now, the second law efficiency is a different case. So if I were to ask you to calculate the second law efficiency, you would have to do entropy balance on this. So there's no mass transfer, so I would have to know the boundary, what is the heat source, temperature of the heat source. So I'd have Qn over Tb, and I have Q out over Tb. Then I would calculate the entropy generated. I'd tell you the surrounding temperature. And you would have to calculate the entire, actual work, which is the area under the curve. And then you could use that, the actual work, the area under this curve. So this is work actual, right? And then my work reversible would equal my work actual, this power producing minus T naught S gen. And then I would get S gen from second law. And then in my second law, I would have Qn over T1 minus Qn, or out, over T2 plus S gen equals delta S in my system. What is delta S in my system when I go through this cycle? 0. And then I would just need to know Q1, these temperatures. Well, I already got those temperatures from there. So you could see you could do this whole thing with the second law efficiency, but it's much more involved. So I don't want to force you guys to do that on a test. It's too much. But you can do a second law, and so I just start with the second law efficiency, right? Work useful over work reversible. For the Brayton cycle. Get the area under the curve. There's no surrounding work, so for a cycle, you end up with the same. So my work reversible out, my work useful out is the same as the work actual out, which is the work in that diagram. I know my heat in, my heat out. I just need to know the temperatures at which heat is coming in and the temperature at which heat is leaving, so I can divide. I know what T1 and T2 are. Those boundary temperatures.
And for power producing, is this work actual plus TOS gen?
Oh, yeah. Thank you. Yeah, because you want this number to be bigger and bigger and bigger and bigger. Yep, thank you. But you get the general idea how you can calculate the second law or thermal or the first law. You can do the first law of efficiency too. I just did thermal because there's this simple expression, and it gets you to think about entropy and energy balance. This is even a better problem, but I think that's beyond the scope of the course right now. Yes?
So what does happen to these graphs if there is mass loss?
Let's just think about what happens to this graph if I have mass loss. Okay? This one right here. I say I go through one cycle, and at some point I get to this high temperature, and I start getting a crack in the wall, and there's mass loss. What happens?
Your volume goes down.
Pressure goes down, and let's just draw it in green. Am I going to be able to get to the same volume? Probably not. I lost mass. I'm going to get back to the same pressure, but then when I come back, so here when I compress it, I guess I can get back, I get a smaller area. So I get something more like this green one.
Okay. So it's going to come back to the same state. It's just
Yeah, well, it depends if I define this as the surrounding pressure. Okay, so if I say P1 is the pressure of the surroundings, but if this pressure is greater than the surrounding pressure, then I'm going to come back down there, and I'm never really going to, so it's going to change a lot. So this pressure has to be, as soon as I have a crack in the wall, then it's going to be coupled to what the surrounding pressure is, and this will change quite a bit.
Okay.
Does
So
a
we
crack
assume
change?
that it's pressure?
I'm not going to ask you a question like that.
Okay.
Does a crack change your system boundary?
Well, it changes the whole boundary condition,
Yeah.
right? You have mass transfer. Everything gets more complicated.